Hi, everyone. Today I want to talk about a protocol that we have been working on for the past couple of years to protect data that we send to Firefox client in the wild. And this is a mechanism that we call content signature that we have built specifically for Firefox. And my goal is to explain a little bit how we built this protocol, what kind of challenges we had to work through, and maybe give ideas to other people who might want to be building the same type of things in their application. So Firefox, since the beginning of Firefox, has had an update mechanism that we use to release new versions of Firefox to all of our users every time we release a major version, so regularly every 6 weeks. And this update mechanism takes the output of our release engineering infrastructure, will create a set of binary files, hundreds of them per locale, per platforms that we support, and we will ship and distribute this update to our users to bring them to the next major version of Firefox. And this mechanism is also very heavy and requires a lot of people to do a lot of work to exercise it. So we have another mechanism that is add-ons, Firefox add-ons, that is a little more lightweight. And typically add-ons are written by developers that are outside of Mozilla to extend functionalities of the browser. And, but we also use it internally to develop certain features that we feel should be in their own components. And we want to distribute them outside of the normal release cycle, so we use add-ons for those. But in recent years, we've had a third type of data that we wanted to push to Firefox, and those are data collections. And data collections could be anything from an entry in a certificate blacklist to safe browsing data to sometimes A/B testing experiment that we want to run on a small cohort of Firefox users. And so the challenge here that we faced is essentially how do we secure that third type of update. Our regular updates, the one that we release every 6 weeks, are protected with a PKCS1 signature. We use hard-coded RSA keys to sign these updates, and the Firefox client will verify these signatures every time it retrieves the updates. Add-ons are also signed. We use a PKCS7 signature, and that uses an internal PKI that is private to Firefox to essentially issue certificates that sign add-ons and gets verified when installed in Firefox. But for data signing, for verifying the integrity of data retrieved from a web API, there are no good solutions. The industry best practice for this problem is essentially to put your web application at the edge of your infrastructure where clients can talk to, typically through a load balancer, to have HTTPS enabled on that API so that you can verify that the connection is secure, and hope that your web application doesn't get hacked. But that has mainly two problems. The first one is HTTPS interception. And that is actually, as I'll discuss, a real issue for us that we want to cover. And the second one is the compromise of a web front end, of that web application that sits at the edge, is a very big issue for us because if it is compromised, it can be used to push fraudulent data to all of our users. So I'm going to cover both of these. HTTPS interception is a real issue on the internet. This is data from a study that was run last year in collaboration with Google, Mozilla, Cloudflare, and a few universities to evaluate exactly what percentage of connections are being intercepted and potentially modified. And this is data that we measured on our update service. So when Firefox clients on your laptops make a connection to our update service, we actually measured that 4% of these connections were potentially being intercepted and so potentially modified. In some countries, that number goes up to 15%. So that means that for us, this number is massive. Like when you take a population of users the size of Firefox, we're talking millions of users that are potentially at risk. So it is very important for us to have mechanisms that guarantee that we can ship updates to our users securely and that our users are not going to download and install fraudulent updates. That's the first problem. The second problem is the web application security one. It's essentially a question of balancing development agility and security. Most of our web applications are written in modern web frameworks because we want to give our developers the ability to write them quickly to improve them quickly. And that means that they will use the latest flavor of Node.js, of Python, of Go, of those modern programming languages. And those web frameworks, they evolve too quickly for us to really be able to review them. And so we don't really have a way to guarantee that the latest version of Django, for example, will not have any security issue that puts our users and our services at risk. And even if we could review the latest version of Django, and the Django team does a great job at this, those applications also have major risks in the supply chain, in the list of dependencies that they will import in their web applications. So we have this situation where, from a software engineering perspective, it makes sense to allow for development agility, but it also poses a number of risks to the security of the infrastructure. So we actually tried to find a model where we could allow developers to have that agility, but at the same time, apply sufficient security so that if the web application is compromised, data cannot be compromised. So this is content signature. And a content signature guarantees the integrity of data collections that we send to Firefox. It does not protect confidentiality. It does not protect availability. It also does not protect against replay of bad signature. And we left those out of the design of content signature for simplicity reasons. Inside of Firefox, you might very well have a mechanism that prevents regressing to approve a version of the collection, but content signature itself does not provide that security. At a crypto level, and I'm not a cryptographer, but we have some very good cryptographers at Masada who came up with these primitives. A content signature is an ECDSA signature on the P384 NIST curve. We calculate a hash of the data using SHA-2 and we sign that hash with ECDSA. We get out of that RNS values that we encode with base64 URL safe. And what you see at the bottom of that slide is a little blob of data that is an actual signature. So it's fairly short, fairly lightweight, fairly easy to add and to send to our users without adding a whole bunch of data. The signing relies on an internal PKI that is private to Firefox. We sign data using end entity certificates that are issued by that PKI. It's the same one that we use to sign add-ons, except that we created a separate branch for it that is dedicated to the namespace contentsignature.mozilla.org. And we use certificate constraints to isolate that branch. And when Firefox will verify a signature, it will actually download the certificate chain using an X5U value in the signatures that tells it where to download it from and retrieve these certificates. So in concept, it's very, very similar to how TLS works, except we re-implemented it at a higher level and focusing on the data instead of the transport layer. There are two ways we can deliver content signatures to Firefox users. The first one is in an HTTP response header. So imagine you have an API response that is the body of your HTTP response. And we sign the body of that entire response, and we put the signature inside of the headers. And if Firefox retrieves the HTTP response and sees a content signature header, it will verify the body with the signature that's in the header. And that's great because it's completely transparent to applications, but we actually want to have a little more flexibility in how we transport and verify signatures. So the second method is the one we use the most, which actually places a signature inside of the JSON document that is returned by the API. And we use that, for example, to return responses on partial collections. So for example, if you have a certificate blacklist and your Firefox client may be 2 or 3 versions behind, when it talks to our API, we will only send you the data entries that you're missing. And the signature, however, will be applied on the entire collection and not just these 3 entries. So Firefox will recompile the original full collection and then verify the signature in that entire collection, which is why we transport it in the document. So how does it work when we verify content signature? Firefox makes a call to a web API that we host and retrieves signed data. It will parse that signed data and retrieve the signature and retrieve the X5U value that locates the chain of certificates. And then it will go talk to our content delivery network and retrieve that chain of certificate. And that's just a text file with the end entity certificate, the intermediate, and the root. It will then parse that chain and verify that the end entity was signed by the intermediate that was signed by the root. And then it would compare the common name of the end entity with its application or the application name it expects. And that's similar to how TLS verifies that the certificate you're getting matches the website name that you're connected to. So for example, if you're retrieving a certificate blacklist, Firefox will expect a certificate that's named 1crl.contentsignature.mozilla.org. And that allows us to sign data with their own certificate, with their own branch, and one application cannot use its certificate to sign data for another application. And if everything passes, it will verify the signature and load the data and pass it to the next level. So one interesting aspect here is the operational security of this infrastructure. What we really wanted, I talked about this with the web application security point, is to have an air gap between the web application front ends, the one that are exposed to the internet and potentially exposed to compromises, and the layer that applies the signature. And the way we do this is essentially by having admin panels that are completely isolated from the internet. And when we want to make a change to a data collection, a developer will go into that admin panel and propose a change. It will be a peer review, a dual sign-off step. And that admin panel will be talking to an internal signing service that will sign the data and give it back to the admin panel. And that part of the infrastructure is completely air-gapped from the internet. That data will be written in a database, and the web application front end will have access to that database in read-only mode, so that even if it's compromised, it can only read data that was already signed. It cannot modify that data. I'm going to talk a bit more about signing certificates later, because there are interesting problems here, but we essentially try to use short-lived certificates so that in the unfortunate event that one of the certificates would be left on a deprecated server, then it wouldn't be able to be reused down the road by an attacker. And like most certificate authorities, we store the root of our PKI in offline HSMs, and we require physical access to issue new intermediates and renew those intermediates. So some of the interesting problems we had to solve implementing this protocol are first checking certificate validity, measuring and getting notifications on verification failures, and preparing for emergency revocation. And you will see that those are very, very close to the kind of problem we see in the web PKI. Certificate validity essentially is a step that a client will take to verify that a certificate is currently valid and can currently sign data. The problem with this is that a significant portion of clients have clocks that are out of date. So on this graph, by the way, uses a logarithmic scale, so be careful how you read it. But the spike on the right side of the graph in the green box indicates users that are at the current time, that are up to date. And that's the majority of our users. That's really 98.8% of our users. And then inside of that green box, we have about 1% of our users that have clocks that are within 30 days of current time. They could be in the past or in the future. They don't have accurate clocks, but they're not too far out. And then we have 0.1% of our users that have clocks that are completely foobar, like completely outside of those 30-day windows. And for those users, chances are that their experience on the internet is already pretty poor, because they can probably not connect to most websites. But we are in a situation where we actually want to still be able to update those users. We don't want to leave them behind, because for us, even 0.1% of users is still a fairly large number of users. So we're not just going to cut them out of the internet. But we had to make a decision between allowing clients to verify certificates that are already expired, which potentially could allow an attacker to steal a certificate and reuse it 6 months from now, or leaving some of our users behind. And we try to find a middle ground with essentially using 90-day certificates, but only using them for 30 days. So we don't use them, we just use the 30 days in the middle. We let the 30 days prior and the 30 days after unused, so that clients that are a little bit outside within 30 days of an accurate clock can still verify those certificates. And that was an important design decision when we were building this, in actually being able to measure how many users are going to be left behind once we implement this protocol. And that's also the reason why we haven't yet implemented content signature on some of our channels that we think are too sensitive for this, where we really don't want to leave users behind. So more work is needed here to understand exactly how big a population we would be leaving behind if we apply a strict certificate validation to some of our channels. Measuring validation failures is also a very interesting problem. If you apply a content signature or any sort of signature method to your product, you want to know how many people are failing to verify those signatures. But that's actually really hard to do. TLS doesn't have a good mechanism for this. And in our product, in Firefox, we have something called telemetry that will send a message to us on certain events. And some of the future work we want to do here is have better telemetry data when signatures fail to verify, to understand why that verification failed. It could be because the client had a bad clock, but maybe because that client is in a situation where the connection is being intercepted and modified. So there is more work to do here as well to really understand the situation in which a user is not able to verify content signatures. And finally, revocation. If you follow the web PKI a little bit, you will know that revoking certificates is a hard problem, mostly unsolved. And CAs have tried to implement certificate revocation lists and OCSP, but those have their drawbacks. They don't work really well. So browser vendors have implemented their own revocation techniques. Firefox has one CRL. Chrome has another one. We all have a way to say this certificate authority or this intermediate or maybe this end entity is no longer trustworthy, so we're going to tell all of our users to stop trusting it. And we wanted to be able to reuse a similar mechanism for content signature in the event that one of our intermediate or end entity certificate would leak or we would get attacked, and be able to protect our user by saying you should no longer trust that particular signing certificate. Interestingly here, there's a bit of a chicken and egg problem where the one CRL data collection itself is signed with content signature, so technically it could revoke the certificate that signed itself. So we had to work around a couple of interesting issues here. And then there's a problem of revoking the root of the internal PKI itself. What happens if the root itself leaks? And for that, essentially, we will have to issue a major code change to Firefox, issue a new release of Firefox, and essentially replace that PKI entirely. We know that we will be leaving users behind if we do that, so it's a dramatic event, but we have somewhat of a solution should that ever happen. So if you want to do something similar in your product, it is actually not that hard to do. In terms of implementation complexity, it was much easier than I had expected. That may be because Firefox already has all of the components to manage a PKI due to the web PKI and HTTPS. So the code changes in Firefox were actually very small. The main patch is only 800 lines. So that's very small for a new signing algorithm. We wrote a backend to sign that data, which is a little bit bigger, but still nothing too ridiculous here. And the team that worked on this was essentially myself and 3 other people. We're part of the core design team and implementation team, and we had another 4 or 5 people help with the testing and implementation and maintenance of that project. So again, not something that required a very large team or a lot of resources, and I would really invite any organization that publishes products and actually talks to web APIs to consider this kind of mechanism. So this is content signature. The code is open source. You can check, obviously, the Firefox code in the Firefox source code repository. And if you want to take a look at the backend, it's online as well. And I'm happy to take any questions.